Hello and welcome back again to our channel, Tutoring Made Easy. I hope each and every one of you is doing great. In today's video, we are going to take a look at functions, a comprehensive lecture on functions. If you take a look at our videos, we've already done some little bit in here of topics on functions and some snippets here and there and solving problems here and there on functions. But today, we want to provide you with a go-get-to video on functions where all the things you need about function, all the knowledge that you need about function will pretty much be in this particular video. So if you are ready, let's zoom straight right in. But before we start, I will want to give us the content of the video. So we said we're going to look at functions. We're going to start with functions. That's the main topic. But we'll be looking at the first thing we're going to be talking about is definition. We'll talk about the definition of functions. And then the second thing, we're going to look at the types of functions. We'll look at types of functions. And then the third thing is that we're going to look at relations. We'll look at relations and functions. And then the next thing we're going to take a look at is we'll look at a functional notation. When we say a function, how does a functional notation look like? We're going to be taking a look at that. Then the next thing we're going to be looking at is to find the domain. When we are asked to find the domain of a function, what does it mean, or how are we able to arrive at that? The next thing is to find the range of a function. The next thing too is an inverse, to look for the inverse of a function. Look for the inverse of a function, and then we'll look at composite functions. We'll look at composite functions, and then we'll continue with we're going to continue with finding we're going to maybe rational functions. We'll take a look at maybe rational functions. Yeah, we'll look at rational functions, and then how we can find the domain of a rational function. All right. Also, how we can find the range of a rational function. And then we can continue by looking for the zeros. We can be asked to find the zeros of a rational function. The zeros of irrational functions. We can be asked to look at that. And then finally, we'll crown it all with partial fractions. So it's going to be a very long video, but I'll do my possible best to move at a pace where understanding and clarity will be there, and to make things easy for you. One thing is, each step of the way while we're going through these concepts, I'll be providing us with examples so that we can be able to have meaning to the concept to become easy for us to understand and appreciate what we are doing. Also, look out for our short videos. Within our short videos, the goal is to be solving problems, to solve as many problems. Every little concept or topic that we've taught so far, our intention is to provide a problem and solve that problem so that you can be having question and answers or practice questions alongside the lecture that we are providing for you. All right. So I hope you're doing well, though. I hope you're doing well. If you're doing great, that's great. And then we are going to zoom straight right into functions. So let's start with a function. What is the definition of a function? So we look at definition. When we say a definition of a function, we're basically saying that it's a mathematical expression. All right, a mathematical expression. So a mathematical expression. So for a function to exist, it has to be a mathematical expression first. It's a mathematical expression, and on top of that, it's of the form something like this: f of x. Sometimes you see f of x, you see something like f of x, you see something like g of x, or you see h of x, or you see p of x, or you see something like this, maybe f of x like this to something. All right, or you might see y, or you might see something like y is equal to something, or p is equal to something. It's a function, maybe y of x or p of x or m of z or n of a. These are all functions. So a mathematical expression of the form these form is known as a what, a function. A function. Now we said that the next thing after definition of a rational of a function, we said the next thing is to look at the types. We said we want to look at the types. We want to look at the types of functions. We want to look at the types of functions. The types of functions. That's what we are trying to achieve. Then we said that the first type of function we can talk about, the first one we can talk about is what we call the linear. It's known as a linear function. It's known as a linear function. It's known as a linear function. And the next one we can talk about is what we call the polynomic. It's known as a polynomial function. A polynomial function. And under the polynomial function, we have what we call the quadratic function. We have what we call the quadratic. We have the quadratic, okay, function. We also have what we call the cubic function, and then anything of the nth degree term, the nth degree term function. All right, and then that'll be for the polynomial. The next one, the next category will be the logarithmic. It will be the logarithmic. We can talk about the logarithmic function. So we have the logarithmic logarithmic function. I think I'm having a slip of tongue here. So logarithmic function will be the next one, and then we cap it off. We keep going, and the next one is what we call the exponential function. The exponential function. All right, and then the next one after exponential function is what is called the periodic. It's known as the periodic function. We have the periodic function, and then we have after the periodic function, we have what is called the trigonometric function. The trig functions. All right, we have the trig functions, and then after the trig functions, we have what we call the absolute value function. We also have what we call the absolute value function. So we have the absolute functions, and then we also have what we call after the absolute functions, we have what we call the odd functions. We have what we call the odd functions. All right, we have what we call the odd functions. Odd functions. We also have what we call the even okay, even functions. And then we kind of squeeze in the other function that is known as the composite functions. We'll take a look at each of them. Don't worry. We're going to look at what is also known as a composite functions, a composite function, and then the last thing is going to be the rational function. So we have a composite function, and then a rational function, and maybe a rational function. All right. I know I've thrown words at you, but we are going to go into each of these and look at what they they tell us. What are they telling us? Now with a linear function, we are saying that it's supposed to be of the form f of x is supposed to be equal to what, a plus bx. Anytime you see a function of this form, then it's of a linear function. And if it's a linear function, it will be like of this form, right? This is the y-axis. This is our x-axis, and then it will be like a line, like a straight line, or it could be just like this, maybe like that. Okay, so f of x is equal to a plus bx. It means it's a linear function. Now, what about the quadratic function? With the quadratic functions of the form f of x should be equal to ax squared. Anytime you see an x with a squared as the highest term in that particular function, then it is a quadratic function. So ax squared plus bx plus c is our quadratic functions. And if we are drawing that, it will look like this. You can have it. So there's a quadratic function for you. Now with a cubic function, on the other hand, it will look like this. And f of x is equal to maybe ax cubed. Cube is the highest degree term. Plus bx squared plus cx plus d gives us a cubic function. Now with the nth degree term of a function, we are saying that the f of x is going to be equal to ax to the power n plus bx to the power n minus 1, like that, plus dot 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 maybe c to the power x to the power c, all right, to the power 0, like this. All right, so that's the nth degree term because this is the highest. With a cubic function, the 3 is the highest. That's what makes it a cubic function. With a quadratic function, the squared here makes it a quadratic because that's the highest term in there. And then with a linear function, the term here is 1. You can see that it's 1. That makes it what? The linear function. Now we are going to go into what we call the logarithmic function. The logarithmic function is usually of the form maybe y is equal to log, or let's say, let me take it again. I'm going to have maybe g of x. We are saying that maybe g of x is equal to log of x to the base a. Log of x to the base a. That is a logarithmic function. And usually they are of the form, they take the form like this. With the log functions, they take this form. The log functions take this form. You see something like this. Something being drawn like that. Let me take the white color, maybe like this, in this form. And you know that that is your logarithmic function right there. Now with exponential function, on the other hand, we are having our m of x is equal to e to the power of x. And with that, our drawing will look like something like this. We have our y-axis, we have our x-axis like this, and we can see that the drawing it's a little different. The drawing is a little different, where we're going to have something like this, and this is our e to the power of x. E to the power of x. Now with periodic functions, we are looking at a function that repeats its values at regular intervals. So it repeats, let me take that. This one repeats its values at regular intervals. And when we hear something like that, that is similar to like the trig functions. You know, the trig functions like the sine x, cos x, tan x, they are like that. We'll look at the trig functions. I think the next thing we'll look at is the trig functions. They repeat itself at regular intervals. Now with trig functions, if you take something like this, the sine, let's say the sine, when you take something like sine x, sine x is like this. You will see that at sine x, you have something like this, and it's starting to take its shape from right here, from the origin, like this, and then it keeps going at regular intervals. You see that changes at regular intervals. The gap between here and then here are the same. Regular intervals, it changes like that, like an economic cycle. Like an economic cycle. Now, we also have cos x. If you look at cos x is a bit different, but it's also going to be having changes at regular intervals. It's going to have changes at regular intervals, and let this how it's going to look like. Cos x instead will start from somewhere here, and then drop down, and then keep going, drop down, keep going like that, and like that, and like that. All right, that's cos x, and then tan x is a bit different. Our tan x is a bit different. So with tan, we are having something like this. With tan x, you're having something like that, something like it's kind of like dancing, like that, and then it will be going like that, something like it's dancing kind of. All right, so that's tan x. I hope so far you are following the types of functions. We've looked at the linear function, a plus bx. We've also looked at the polynomial function, which is this here. We've also looked at the cubic function, so this term ax cubed plus bx squared plus cx plus d, and the nth term, which is this one with the nth term function. And then we are looking at the logarithmic function. This is the logarithmic function. This is the exponential function. And the periodic functions are like the trig functions. They repeat their values at regular intervals, and we looked at the trig functions. Those are the drawings we are having here, and there. Now the next thing is the absolute function, where you have something like this. It's of this form like that. That's how it looks like. The absolute function, we are saying that with the absolute function, we are saying that, let me write it right here. I'm squeezing it in here. Let's say you have f of x is this, the absolute value of that, or the modulus of that. We are saying that the x there can be, the x there, we are saying can be, it's positive, like this, if x is greater than or equal to 0, and it's also negative x if the x is what, less than what, it's less than 0. All right, so that's the absolute value function. You're saying that when you take the absolute value of a certain function, take the absolute value of a certain function, it is positive when the x is greater than and equal to 0, and it is negative when the x is less than 0. That's the absolute value function. Now, with the odd function here, we are saying that with the odd function, we are saying that negative f of x should be equal to f of negative x. All right, f of negative x. That's what we are saying. So if you take something like the s cube, right? If you take something like the function s cube, when you do minus x cube, you get minus s cube. If you also do the x itself to be the negative, right? Negative x, and you cube it, you are still going to get negative s cubed, and they are the same. But with even function, on the other hand, all right, let me go here a little bit. With even function, we are saying that with odd function, we are saying that if you have negative f of x, is going to be equal to f of negative x. So if you take, let's say, the function, let's take the function is equal to s cubed, right? Now, we are saying that minus this function, let's say f of x, let's say minus f of x is going to be just negative into the x cube, right? And we are going to get negative s cubed. But if we take f of negative x, it means that this s, the x itself is negative, so it's going to have negative x itself, and then we cube it, and that's going to give us negative x times negative x times negative x, and this negative x times negative x gives us positive x. We multiply by negative x, we multiply them, and we are still going to get what, this one is going to give us x squared, and we're going to get negative what, x cubed. All right, so you can see that this and that, they are the same. That's why we're saying that negative f of x is the same as f of negative x. Anytime we see something like that, that type of function is an odd function. So we are saying that an odd function, an example of an odd function is when you have a function x or s cube or sine x. These are examples of odd functions. Now, when we look at, let's take a look at maybe even, let's take a look at maybe an even function. With an even function, we are saying that if you have f of x, let me write it in white. If you have f of x like this, we are saying that it should be equal to the even function should be equal to what, f of negative x. F of negative x. So if we also have a function of x squared, let's say x squared. Let's say you have f of x is x squared. We are saying that this f of x, which is x squared, so is the same as f of negative x, which means that the x itself here is negative x. So this x here is negative x, and we squared, and that's going to give us negative x times negative x. And these two will give us positive x squared. And you can see that f of negative x, this one, is equivalent. You can see that it's equivalent to this f of x, which is x squared. They are the same. That shows us that that is what, that is our an even function. An even function, an example of an even function, if you have absolute values of x, or you have x squared, or you have the cos function, these are the even functions. All right, and we said that the odd functions are what? The odd functions are what? We said it can be x, it can be s cubed, and it can also be sine x. I hope this kind of like this kind of helps. I hope this kind of helps. Now we're going to go into what we call the composite function. Now when we say a composite function, when you and I talk about a composite function, we are talking about bringing two functions together. So let's say we have an f of x is equal to a plus maybe bx, and you and I have another function h of x, which is equal to negative m plus maybe b of x, right? Like this, we can be able to have a composite function where we are saying that, can we look for h of x plus f of x? And we know that this h of x is the minus m plus the b of x plus this f of x, which is a plus bx. And we can have our what? Minus m plus a plus bx, because we are not changing any sign, because there's no equal to sign in whatever we are trying to do. And that makes this one 2bx plus a plus negative m, like this. All right. So once we have joined these two functions together, it's called a composite function. Or sometimes we could be asked to look for maybe f of h of x. F of h, that means that we're going to start f. We're going to write f. And in f, the first thing we have in f is a. So we're going to write a. All right. We're trying to write f of x. We're starting with this function f. The first thing we're going to write is f, which is a. We're going to start with a. And the next thing in f is b. We write it b. But the moment we see an x there, we don't write that x. That x is the whole of this. The h of x is the x. So wherever we find x in the f of x, we put h of x there. So that's going to be a bracket, and the h of x is minus m plus bx, like this. And that's going to give us a plus, we said plus b into minus b plus bx, and that's going to give us a minus bm, because this is going to multiply this, and the negative will affect this, and then the plus b will multiply this, giving plus b squared x, and that's giving us another type of what? Composite function. So when we say composite functions, when we are bringing two or more functions together, that's a composite function. Now the last type of function that we're going to look at together is what we call the rational. We call it the rational, and right, the rational function. What is a rational function? It's a function that is a form of fraction. It's a function, okay? That it's a function in the form of a fraction. So we can say that it's a what? It's a fractional function. A fractional function. We can easily say that it's a fractional what? Function. Now, when we say it's a fractional function, what do we mean by that? We know what a fraction is. A fraction always has what? It has a numerator divided by what? A denominator. That's what makes it a fraction. But what makes it a function? What makes it a function is that the numerator is maybe a function, maybe x squared minus 1, divided by the denominator, which is 1 plus maybe x, like this. So that means anytime you and I find two functions that are on top and another one is below, then that is a rational function. So we've taken a look at the definition of a function, which is a mathematical expression which is of a form, maybe f of x, g of x, h of x, all right? And we said that the different types, we have the linear function, we have the polynomial functions, which has quadratic, cubic, and an nth degree, and we also have the logarithmic function, we also have the exponential function, we have the periodic functions, which look like the trigonometric functions, we also have the absolute value function, where it is positive value if x is greater than or equal to 0, or it's a negative value if x is less than 0. And then we also said that the next type of function was the odd function, where we said that if negative f of x is equal to f of negative x, and the types of functions of such functions, the sine x or x cubed. The even functions, we said, is f of x is equal to f of negative x, and those type of functions are cos x or x squared of the absolute value of x. Composite functions, another type where we bring all functions together, or the rational function, which is a fractional type of function. I hope you're enjoying yourself so far. And I hope everything is coming to play. Everything is coming clearer and clearer for you. And I'm happy if that's the case. If it's not too clear, I'll love that you pause the video, take a little break here and there, come back, refresh, continue. Or sometimes you can pause the video and go back to the video and see everything might come clear to you. Now, at this moment, if you haven't yet subscribed to our channel, it'll be a very great thing to do for us, to help us grow this channel together as a family. But if you've already subscribed to our channel, then thank you so much for supporting us. We are going to continue. And to continue the video, we are going to be looking at what we call the relations and functions. We are going to look at relations and functions. And what do we mean by that? In many situations of ordinary life, we are concerned with relations which exist between the elements of two different sets. So you have two different things and want to establish how they relate. How are they going to be relating together? All right, how do you relate it together? Let's say John is the father of maybe Mary. Maybe John is the father of Mary. There's some kind of relation that we have John and we have Mary, and we are trying to establish some form of relationship. Okay, or we can say that Caroline is the wife of Eli. All right, Caroline is the wife of Eli, and these are two different people, Caroline and Eli, and we are trying to see if there's a relationship that exists between them. All right. We can also take a look at maybe it's a student. Maybe we can look at maybe a student. All right, and we can look at the student's city. All right. So we take a look at maybe John, and we say John is from Boston. All right. Or we can say that Mary is from California. Oh, sorry. I said city, not a state. Sorry about that. It's from San Francisco. So this is Boston. It's from San Francisco. Or we can say that Eli is from, sorry, is from maybe Toronto in Canada. Or we can say that Kezia is from a city in Australia, maybe Sydney, like that. And we are trying to establish a relationship. We're trying to establish a relationship between these, right? Or somebody's from London, okay? Ezekiel being from London, like that. We're trying to establish what the relationship. So there are different types of relations in the different types of relations we have. We have what we call the there are different types of relations. We have what we call the many to many relation. We have the many to many relations. And what do we mean by that? It means that you have something like this. You have something here. You have something also here. All right. And the things that are in here maybe you have six. Let's say you have six and you have seven. And we also have maybe 2, 3, and 5. Here we have many here. All right. Many to many. All right. Many to many. We have many things here. Right. Many things in here. And then there's also many things what? There are also many things what? In here. Now we are seeing that we can, when we take this guy, we can map the 6, all right, to this 2. All right. We are seeing that 6 has a relation with the 2. And that same 6 can relate to 3. And okay. And that same 6 can relate to what? This 5. So it is many to many. This single guy 6 is related to many things. And this 7 also relating to many things here. You can see there's different things here. That makes it a many to many relation. Then we also have what we call the one-to-one. We have what we call the one-to-one function. We have what we call the one-to-one function. We have what we call the one-to-one function. All right, the one-to-one function. And in this case, you have, let's say, 3 and 4 here. And let's say we have, let's say, 9, 18, 9, 18, 27, 8, and maybe 16, for example. All right, but this time around, the difference is that because it's one to many function. This 3 can map this and will not map any and may not map a different thing again. Right? Is this 1, all right, this 1 mapping to this 9, and this same 3 mapping to 18, this same 3 mapping to 27, this 4 mapping to 8, and this 4 mapping to what? Mapping to 16. All right. So it is 1 for everyone. It's mapping to many things. Each one is mapping to many things, like that. Each one mapping to several things. Each one mapping to several things, like that. All right. Now, the other one is many to one relation. We have the many to one relation. Many to one relation. Okay. And that one we can have maybe you have, let's say, 12, 15, 24, 36, and 45. And then maybe the other side is just 5 and 12. Picking the white thing. We are saying that many to one mean that from here, from 12, it is mapping is 12. Okay, and then this same 12 is on the receiving end. That means a different number like 24 is mapping to it. All right, so it's many to one, many to one. So this one is receiving many things. All right, this one is receiving many things. The 40, let's say the 36 is also going to the 12. So this is many. This is many. This mapping is many to this one. The map is many to this one, like that. That's what we mean by many. It means that you are relating from many things to one particular item. That's what it means. One from many things to one particular item. So one item is receiving many things. So it's many to one. It's many. It's many to one. It's many to one. All right. All right. So now let's also take a look at um one-to-one relation. We also have one-to-one relation. And with that one, you can have maybe 1, 2, 3. And we can also have maybe 3, 6, and what? 9. And it's 1-to-1. There's no repetition anywhere. That's the one-to-one relation. Now, let's take a look at maybe the functional. Let's look at the functional notation. The functional notation. The functional notation. So that we say that given that, okay, we're going to take a look at what functional notation. Okay, the functional notation. So that the functional notation. So if we are given that f of x, all right, f of x is, let's say, 2x squared plus 3, right? And then by definition, f of 1, by definition, f of 1, wherever we see x, because this is f of 1 and this is f of x. So wherever we see x, we put 1 there. So we're going to get this x, which is 1 squared. What is the x and then the squared plus 3. And then we're going to get 2 into 1 plus 3. And we're going to get 3 plus 3, which is equal to what? Which is actually equal to 6. Then by definition, f of 2, we keep doing that. F of 2 is going to be 2 to the power 2 squared plus 3. And this 2 to the power 2 into 4 plus 3. This gives us 8 plus 3. And that gives us what? 11. That gives us what? 11. That gives us 11. Now, so we should know that f of 1 means the image of 1. The f of 1 is the image of 1 under the function f. The image of this one under the function f. We should just be mindful. We should be mindful of that. Now, since we are done with the functional notation, let's take a look at maybe domain. If we are being asked to look for the domain, maybe we are being asked to look for the domain. We've already looked at, I think, the types of functions, right? We've looked at the types of functions. We are going to look at maybe the domain. If we have been asked to look for the domain of a function, how does that one work? So let's look at the domain. We have been asked to look for the domain of a function. The domain of a function. The domain of a function. How does that one work? The domain of a function. And the domain of a function, let's take, for example, let's say that we are being given f, right? F of x maps. This is maps onto 1 minus 2x. Okay? Okay? Or this is the same as whatever I've rated the same as f of x is equal to 1 minus 2x. And I hope you can see that there's a linear function because of this degree term here is 1. Can you see that? So that's a linear function right there. We have a linear function here. So f of x is equal to 1 minus 2x. And we are looking for the domain. Basically, the domain are all values of x. Domain is all values of x. Okay? That makes the function defined. That makes the function defined. That means you can be able to find the function is correct, everything is fine, there's no problem with the function. What are the values that will make the function defined? And if we look here closely, this function can take on any value. If you look at this f of x, it can take on anything. 1 minus 2x, you can put in here negative 1 million into it. You're not going to have any problem. We can put in a fraction here, we're going to have any problem. We can put in a third, maybe 1 minus 2 square root of what 2, or 2 square root of x, and nothing's going to happen. So it means that the domain of this function, the domain of this function, because you can take on all values, is that x is such that x belongs to all. This is belongs, this is belongs, this is x, and this is such that. So we say x such that x belongs to all real numbers. This is real numbers, all real numbers. X such that x belongs to all real numbers, all real numbers. All right. Now let's also take a look at maybe another type of example. Let's say that we are given k of x. We are told that k of x is equal to x plus 5 divided by x minus 3. Divided by x minus 3. And we are being asked to look for the domain of this function. Right? We can see in the denominator, anytime we see something like that, in the denominator, we have x minus 3. If we equate it to 0, we're going to get x is equal to 0. This has to come here. And when it does, the sign here changes. So it becomes plus 3. Why? Because it crosses the sign. It crosses the equal to sign. So we're going to have x is equal to 3. It means that when we plug in 3, we're going to have x plus 5 divided by 3 minus 3. We're going to have x plus 5 divided by 0, right? Basically, this x is also 3, right? So it's going to get 3 plus 5 over 0. We're going to get 8 over 0. And this makes it what? Undefined. It makes it undefined. It means that our k of x, the domain, okay, of k of x, what it means is that it is that x such that x belongs to all real numbers. It means x can take on all values except that x cannot be equal to 3, because when x is equal to 3, that whole function becomes undefined. So x can take on anything, x take on anything, or k of x take on any value, but you can't take on this value here. So this is how you write the domain of a k of x. Is x such that x belongs to all real numbers except that x is not equal to, except that x is equal to 3. Except that, let me wipe that off, please. Except that x is equal to 3, because I've used the word except x is equal to 3. Otherwise, I can write it this way: x such that x belongs to all real numbers, but this x cannot be equal to 3, like this. It's also correct. But the moment I bring except here, I can't cross this equal to, it has to just be equal to sign. I hope that that one kind of helps. I hope that also works. Now we are going to look at the range. We're looking for the range. Let's say we are being told to look for the range, we are being told to look for the range of a function. The range of a function. And we are being given this, let's say this problem here. We are told that our f of x is equal to 1 minus 2x, like this. All right. The first thing we do is that we let what? We let our f of x be equal to y. That's the first thing we do. So we're going to have y is equal to 1 minus 2x, like this. And once we are looking for range, we want to make x stand alone. So let's make x stand alone. And to do that, y will be here, and this will move here, and the sign changes because it's crossing this equal to sign to minus 1 is equal to negative 2x. Now, we will divide here by negative 2, divide here by negative 2. This will go off, and we're going to have y minus 1 divided by negative 2 is equal to x. That means our x is equal to y minus 1 divided by minus 2. X is equal to that. I don't know whether you can be able to see what we have done so far. So when we are looking for the range of a function, we have to make x stand alone. We have to make x stand alone in a function. Or whatever function, whatever variable we are starting with, we are not going to make that one stand alone. It's the variable that is inside the function. So here, we are starting with y. We started with y. We are not interested in that. We want to make this one rather stand alone. So if we have, let's say we have g of x is equal to p minus m, all right? P minus x, P minus x. We'll make this on y is equal to p minus x, but we want this x to stand alone, not this y. That's when we are looking for the range. If we are looking for the domain, we want to look for a situation where we can equal the denominator to 0. The denominator is 0. So I hope that is clear. So now, so far, we have been able to make our x stand alone. We've been able to make our x stand alone. And if that's the case, we can see that our x is the same as negative half into y minus 1. And we can see that y will take on, it can take on all values. Our x can take on, because we are saying x is equal to negative half y minus 1. We are saying that the x can take on all values. Okay? All right? It can take on what? All values. This y will be everything. So our range is y such that y, because of the y inside, y such that y belongs to all real numbers. It belongs to all real numbers. That's our range. That's our range. So I hope you've been able to see how we are able to find the range of. So the range of a function is to rather make x stand alone and find the values of y that make the function defined. But for a domain, we want to make sure we want to look for the values of x, not the values of y, the values of x that makes the function defined. Now, the next thing we're going to be looking at is inverse. How to look for an inverse of a function. How to look for an inverse of a function. So let's look at the inverse of a function. And to look for the inverse of a function, let's take a look at an example. And we'll use the example to solve the problem. Let's say that we have g of x, g like the g of x that maps to 1 over x plus 3. But this time, this x cannot be equal to negative 3. You see why? Because of the denominator here. Cannot be equal to negative 3. Otherwise, there'll be a problem. Now, what we can do is that we can let g this be equal to g of x. And let that g of x be equal to what? Well, y. So we're going to have g of x, which is equal to y, should be equal to 1 over x plus 3. Right? Then remember, what we're going to do after doing that, we have to make what? We have to make y the subject of the relation, right? We have to what? We exchange the values. We just exchange the values. We exchange the values. We substitute wherever we see y. So let's say that we substitute x for y when we get here. So this will become what? This will become x, and then we're going to have 1 over, this is going to be y. So we're going to y plus 3 like this. So we've substituted that. Now, because we've done that, we look for y. Let's look for y in this function. So to make y stand alone, right? What we're going to do is, if you look carefully, we currently have x is equal to 1 divided by y plus 3. Because of this denominator, we'll multiply everywhere by that. So we got y plus 3 multiplying the x on the left hand side, which is going to be equal to 1 over y plus 3, multiplying the y plus 3 on the other side, like this. So that we're going to have x into y plus 3 is equal to what? 1, like this. So this is going to cancel out. Going to be equal to 1. Don't forget, we want y to stand alone. Now, with this, we multiply this, we get xy. This will multiply this, we get plus 3x is equal to 1. We want y to stand alone. So this xy will stand here. It's equal to 1, and this comes here. Once it's crossing this equal to sign, this sign should change. Minus what? 3x. Now we divide here by x because we want y to stand alone. Divide here also by x, and we're going to get y is equal to 1 minus 3x divided by x, like this. Like this. Right? Like this. So now the inverse of the function g of x, we know that we started with g of x. So the inverse is going to be g prime of x, like this. G inverse of x is going to be equal to 1 minus 3x over x. And what do you think we should add? X cannot be equal to 0. Because when x is 0, that becomes a problem. So I hope you've seen that. So for the domain, we're looking for numbers that makes numbers such that it makes the function fine. All right? If there's a number that will make the function undefined, then it will be except that number. It will be except that number. So domain will take all numbers except that number. But for range, what we do is to be able to solve we able to make x stand alone. We make x stand alone. Normally we start with y, so we make x stand alone, and then when we make x stand alone, we look for the values, the domain of that x standing alone function. That's for the range. But for inverse, we right from the bat we exchange y for x, and then we make y the subject. And once we make y the subject, whatever we get y to be in the subject is the inverse of the function. So now we've looked at domain, we've looked at range, we've looked at inverse. Now let's take a look at a little bit of maybe some form of composite. Let's look at some composite functions. Let's look at some composite functions. Composite. Let's look at some composite functions. All right. Now let's say that we have been given f of x to be equal to 2x, for example, and we have also been given g of x to be equal to x squared plus 4, for example. Now we're being asked to look for g, maybe g of f. Now that is going to be written as g into f of x. What it means is that the whole of this thing here, if you look at it, is our x, like this. It's our g of x, right? It's our g of x. So it means that when we are writing g of x, anytime we see x in g of x, it is our f of x. So we are going to start writing g, all right? We are saying that we have g into f of x, like this. So we are going to start writing g, right? We're going to start writing g. What is our g? Our g starts with x squared. Can you see that? But that x there is f of x. So if we are starting with x squared and our x is f of x, what's f of x? F of x is 2x. So write 2x. But remember, we are squaring it. Our is x squared. So this is, if you think about it, this is our x, and we've squared it. X squared. But we are continuing with g. We finish with the x squared in our g of x. The next thing is to add plus 4. So technically, we are going to have 2 squared x squared plus 4. Remember, from indices, don't forget your indices. You have a, b like this to the power n, which says a to the power n, b to the power n. That's what we've done here. This squared to the power of this, and this squared affecting this. So we're going to get 4x squared plus 4. We factor 4 out to get x squared plus 1, and that gives us our g of f. I hope that works. I hope that works. That is when we talk about, when we're talking about composite functions. That's what we mean by that. That is composite function, bringing two functions together. Now let's take one more. I want to do one more composite function question problem, where we have been given g of x, like this, and it is half of x plus 1, and we've also been given h of x to be equal to 5x minus 1, all divided by 3. And we are being asked to look for h inverse of g. We've been asked to look for h inverse of g. And we know that h inverse of g is the same as h inverse into bracket g of x. So we know that when we're writing the h inverse of x, this is the same as h inverse of x. But that x there is our g of x. So when we're writing h of x, when we get our h inverse of x, that x in our h inverse of x is our g. We have to put g of x in there. Don't forget that. So I think the first thing we need to do is to look for h inverse of x. Let's look for h inverse of x first. What do you think? Let's look for h inverse of x first. And remember, h inverse of x is the inverse of h of x. Don't forget that. Inverse of h of x. And what did we say we're going to start with? If we're doing the h inverse of x, what do we say we are going to start with? We said that we first have to what? We first have to take this function. So we have h of x, which is 5x minus 1 divided by 3. You remember that? And we said that we should make that h of x, let's say y is equal to 5x minus 1 divided by 3. And we said we should substitute the x for the y. And if we do that, this is going to be x, is going to be 5y minus 1 divided by 3. And then we look for what? The y. So what we do, we're going to have x being equal to 5y minus 1 divided by 3. Because of this 3, we multiply each term by that. So it's going to be 3 times x on the left-hand side is equal to 5y minus 1 divided by 3 multiplied by 3. And then this is going to give us 3x is equal to, this goes away, and we have 5y minus 1. We want to make y stand alone. So 3x will be here. This one will come here. It will become plus. The sign here changes because it crosses equal to sign. Plus 1 is equal to 5y. And then we divide here by 5, go 1 y to stand alone, and divide here by 5 as well. When we do that, we're going to get 3x plus 1 divided by 5 is equal to y. Can you see that? Therefore, y is equal to 3x plus 1 divided by 5. And this y is our h prime of x, which is 3x plus 1 divided by 5. But we are being asked to look for what? H inverse of g, which we said is h inverse of g of x. So we are going to write h inverse of x. And to write h inverse of x, this is the function here. The first thing we see in the h inverse of x is 3. And the next thing is x attached to it, but that x should be g of x. What is g of x? It is half of x plus 1. So that this is like 3x. This whole thing is like x, 3x. But our x is our g of x we are putting. We are writing h of x in a different way. So h of x starts with 3, and we're multiplying by the x, and that x is our g of x. And then when we finish, we add plus 1 to it. So this is like 3x plus 1. Because that is what is in what? That is what is in what? The h inverse of x. Then when we are done in h inverse of x, all we do is we divide everything by 5. And we are going to have this 3 is going to multiply all that, and we're going to get 3 over 2x. The 3 is also going to multiply the 1. We're going to get plus 3. And then there's a plus 1 there. And we divide everything by 5. We get 3 over 2x plus 4 divided by 5. So we are going to get 3 over 10, because these two come down here. 3 over 10x plus 4 over 5. And then there we have it. I hope this question on composite function has clarified a little bit of things here. A little bit of some form of differences that we don't, maybe it's not too clear. But I hope it is helping. If it's not, please pause the video, take a little break, freshen up, and come back again. If you haven't yet subscribed to our channel, please do us a favor by subscribing so that you can help us grow this channel together as a family. And please, if you've already subscribed, thank you so much for helping us out. Now, the next thing after the composite functions, we are going to go into what we call rational functions. We are going to go into rational functions. Rational functions, we already stated what they are. If you remember, we said that a rational function is a fractional function. I think that's my own definition. A rational function is a fractional function. It's a fractional function by definition. All right? And we're saying that if it's a fractional function, then this fraction has to have what? A numerator divided by what? A denominator. All right? Then that's supposed to be the case. Numerator divided by denominator. But it's a function. It's different from a fraction because it becomes a function because in the numerator you have like a function like this divided by s cubed plus 1 in the denominator. Then this makes it what? A rational function. So anytime you and I are going to see a rational function, there has to be a numerator, there has to be a denominator. So an example of that is maybe x squared plus 2x minus 8 divided by what? X plus 4. This is a rational function because at the numerator there's a quadratic on top, as the numerator, and you also have a linear as the denominator. So the numerator is, this one will be what? An improper rational function. Can you see that? It's an improper rational function. Why do we say that? Because quadratic is bigger and then the linear is lesser in term, because this is ax squared plus bx plus c divided by, this is going to be a plus bx or ax plus b, and you can see that the top is bigger than that. So that would be an improper rational function, an improper rational function. All right, improper, right? But if the top part, if you have, let's say, a linear on top and you have at the bottom a quad, then this is what a proper rational function. It's a proper rational function, and I hope you can see that. I hope you can be able to see that. Now we're going to look for what we mean by the domain. We've already done it. We can apply the same rules that we did. The same rules that we did when we're looking at rational functions. The same rules. We're going to apply the same rules. So we have rational functions, but this time around we are going to look at the domain. We're going to look for the domain of a rational function. The domain of a rational function. It's the same rules we're going to apply. Now, always, if you have f of x is equal to, let's say, 2x divided by x plus 2, always we look at the denominator. We always look at the denominator here, this one. We'll take the denominator and equate it to 0. And x will stand alone. We have 0. This comes here. The sign changes because we cross the sign. Minus 2, we get half x is equal to negative 2. So the domain of this rational function, the domain of this rational function is equal to what? X, such that x belongs to all real numbers. But x cannot be equal to negative 2. Because if x is equal to negative 2, that is going to give us what? If f is equal to negative 2, we are going to have what? 2 into negative 2, this one, divided by what? Negative 2 plus 2. We are going to get negative 4 on top and then 0 on the bottom. And this gives us what? Undefined. So that's why we're saying that this f of x can take on all real numbers, but it cannot be equal to a negative 2. We stated that. Now, let's take another more example. Let's say that you and I are given, let's say, x squared plus 5 is g of x, and is divided by, let's say, 2x squared plus 3x, for example. All right? Now, what we can do, we said that we should always look at the denominator. 2x squared plus 3x should be equal to 0. Now, we're looking for x. Can we see that as a common factor, which is x? It comes out, and we have 2x inside, plus 3 is equal to 0. And then we can say x, this x should be equal to this 0. And then this 2x plus 3, this one should also be equal to 0. We know x is 0. And here is going to be 2x will stand here. 0 is here. This comes here. And the sign changes to minus 3. And then we divide it by 2, divided by 2. We have x is equal to negative 3 over 2. And x is also equal to 0. So the domain, we'll say the domain of this, rational function is what? X, such that x is all real numbers, but x cannot be 0, and x can also not be equal to a negative 3 over 2. This is how we find the domain. We find the domain of a rational function. Now let's look at maybe the range. Let's take a quick look at the range. Finding the range of a rational function. Of a rational function. Of a rational function. All right? And let me wipe I think it's not clear. It's not good. It's not tidy enough. Sorry about that, please. So we are saying that we are looking for the range of a rational function. Domain of a rational function. And this domain of a rational function, let's imagine we have f of x being equal to x divided by 1 minus x. And you remember what we did the other time. We said we should let the f of x be equal to y. Remember what we did earlier on? We let f of x to be equal to y, and then y becomes x over 1 minus x. It's when we are doing the inverse where we substitute y with x. But this time around, we want to make x the subject. We want to make x stand alone. And to do that, we multiply each side by 1 minus x. Why? Because that's the denominator here on the other side. So 1 minus x will multiply y on the left-hand side, and then x divided by 1 minus x. We'll also multiply 1 minus x on this side. We're going to have y into 1 minus x is equal to this will go away, and we're going to get x. We're going to get y minus what? Xy is equal to x. We want x to stand alone. And so to do that, we let the y be here, and we have x on the other side, and this one will come here, and it will change to plus xy. X can be a common factor. We bring it out, and we get 1 here, plus y. All right? And then y on this side. We divide it by 1 plus y, divide it by 1 plus I, and then we have y over 1 plus y is equal to x. Therefore, sorry about that. Therefore, x, the one that is standing on, therefore, x is equal to y over 1 plus y. And then the range is going to be what? We can see that the range, there's a denominator, we have to equate this to 0. So 1 plus y should be equal to 0. And y is equal to 0 minus 1. This will change. So we have y is equal to negative 1. Therefore, the range is y. Okay, we'll look for y, right? The range is y such that y is all real numbers, but y cannot be equal to -1. So with domain, we are looking at x values. With range, we are looking for y values. All right, so let's keep that in mind. That's why we made x stand alone to look for to have y expressed in the x function, and then to be able to look for the values, the domain. So basically the range is the domain of y. Are you getting it? The range, I'll write it somewhere here. The range is the domain of y values. And then the main domain we know is x values. And then the inverse is quickly substituting y for x and then solving for y, and then the y will give you an expression in terms of x, and that will be the inverse right there. So we looked at the range. We've looked at the range, and we are now going to look at zeros of a rational function. Let's say we are looking at zeros. We can be asked to look for the zeros of a rational function, or look for the values of x that make the rational function undefined. They are two different things. Now, let me break it down here. Let's say we are looking for zeros of a rational function. And we are saying that this is different. It's not the same as values, okay, that makes the rational function undefined. What are the values that makes the rational function undefined? It's different questions. So let's take it one after the other. Let's imagine that we are given, let's say we are given x squared plus 2x minus 8 divided by x plus 4. And the question says find the zeros of this rational function. What we do, because we are looking for the zeros of this rational function, we are saying the zeros of, so this whole thing should be equal to 0, because we are looking for the zeros of that rational. This is the whole rational function, and we want to look for the zeros of that. So we need to equate it. That's why we are equating everything. That's why we are equating everything to 0. We're equating everything to 0. And when we do that, because of this denominator, let me write it here. We have x squared plus 2x minus 8 divided by x plus 4 equal to 0. Because of this denominator here, we multiply each side by x plus 4. So x plus 4 will be here. Multiplied by x squared plus 2x minus 8, right, divided by x plus 4, right, is equal to 0 times x plus 4, like this. Now, this will cancel out this, and we're going to have x squared plus 2x minus 8, and then this whole side becomes 0. Now we are left with the quadratic, and we are just going to solve the quadratic. Now the quadratic is -8. There's 1 here, so that's easy. -8. So -8, what do we multiply to get -8? But when we add, we get +2. We get this +2 here. All right, we get +2. So that's going to give us maybe 4 and -2. When we multiply 4 and -2, you're going to get -8. But when we add 4 and -2, we get +2. So because the numbers are 4 and -2, our x plus 4 and our x minus 2, because this side here is 1. If this side is more than 1, we can't do what we are doing here. So that's another trick you can keep in mind. So we are going to have x, which is equal to 0. So x plus 4 is equal to 0. X minus 2 is equal to 0. This is going to be x is equal to 0 minus 4, which is equal to -4. And x is going to be 0 plus 2, which goes to 2. So the values of x, that makes the zeros of the rational function, so the zeros of the rational function, they are what? Are -4 and 2. -4 and 2. Those are the zeros of the rational function. But this same question, let's imagine the same problem. I want to find the values that make this rational function, the same rational function, undefined. What will make this rational function undefined? It is when the denominator is equal to 0. When the denominator is equal to 0, then the rational function becomes undefined. So x plus 4 is equal to 0, gives us x is equal to 0 minus 4, x is equal to -4. That is what will make this function undefined. So the values that make the rational function undefined is when x is equal to -4. But the domain of this rational function will be that x, such that x is equal to all real numbers but x cannot be equal to -4. This is domain. It's different from this answer. This one is the value that will make the whole rational function what undefined. But this notation that I've written here is the domain. So this is the domain. This one here is domain that x, such that x is all real numbers, but x cannot be equal to -4. That's the domain. But this x is equal to -4. When x is equal to -4, that makes the rational function undefined. I hope that clear. So there's a value that makes the rational function undefined. There's a domain of the rational function, all right, and then the zeros of the rational function, all right. So let me summarize that here. So we have rational functions here. We can be asked to look for the domain of the rational function where you say x such that x is the member of all real numbers and x cannot be equal to something. How do you get this? Is when the denominator, you equate the denominator to be equal to 0 and solve and say that x cannot be equal to that number. Then you also have what we call what the finding the values makes function undefined, makes the function undefined, and we are saying that the values of x that makes the function, the rational function, makes rational function undefined. The values of x that makes the rational function undefined is just to make the denominator, just equate the denominator to 0. And that value, if it's x is equal to 4, is the value that makes the rational function undefined. But the domain will be written like this. Now, the next thing is to find the zeros of that rational function. The zeros of the rational function is to equate, make the rational function all equal to 0 and solve. And the values you get make the rational function equal to 0. The last one, aside domain values that make the rational function undefined, or the zeros of the rational function, is to look for the range of the rational function. And we apply the same rules as we have done in the past. Now, because we are done with the zeros and everything, now we are going to go to the next broad topic, which I think will end our discussion, and that topic is known as partial. We are going to look at what we call partial fractions. We're going to look at partial fractions and see how that helps us in our knowledge of partial fractions. So rational function is going to help us to be able to achieve that. We're going to get the knowledge that we need to be able to understand rational partial fractions. So it is rational function that's going to help us have clarity with partial fractions. So let's look at partial fractions. Now, with partial fractions, I'm going to divide it into 3. There are 3 main methods. 3 main methods. But the questions can come in 5 forms. But I want to say 3 main methods. But you can also look at it in 5 ways, so that no matter how the question is thrown, at us, we can be able to still have an understanding, of what we are doing. So I like to say that the method 1, the main method 1, is when you have linear, the type when you have linear factors in the denominator. So in the denominator, linear factors, in denominator, you have linear factors in the denominator. So an example could be, let's say you have 6 all divided by x plus 3 and maybe x minus 3, for example. Now, this is a linear, and this is also linear. So if you have linear factors in the denominator, that's method 1. You're going to apply method 1. And to do that, all we have to do is take a constant, a variable, maybe a. The variable is a, which is a constant, and divide it by each of this linear. So this one will take the x plus 3, and then there'll be another variable, b, or a constant, and we divide it by this linear, x minus 3, like that. So what do we do? Now, can you see that this whole thing here, it's a fraction? I don't know whether you can see that. There's a in the numerator, and then and then x plus 3 in the denominator. This also is a fraction. I don't know whether it's very clear. This is also a fraction. B in the numerator, x minus 3 in the denominator. And the sign in the middle is addition. So if we're having a fraction adding another fraction, we are back to the significance of fractions. So what we do, we multiply this by that, and we multiply this by that, and multiply this by that. So what do we do? First, let's multiply the a. We're going to have this same 6, x plus 3 here. Don't forget to write that first. And then equate it. And then we have a multiplying the x minus 3. We said let the a multiply the x minus 3. Plus the b will multiply the x plus 3. Can you see that we are applying what we know in fractions? And then we divide it by the denominators, which is x plus 3, x minus 3. Can you see that? Once we do that, we can see that the denominators here are equal. And there's an equal to sign in the middle. So that means that the 6 is also equal to the numerator. The numerators are equal and the denominators are equal. That's what it means. So basically, we're going to say 6 is equal to the a into x minus 3 plus b into x plus 3. Now we can pick 3 here. When we put 3 here, this whole thing will become 0. Can you see that? When x is equal to 3, this whole thing goes to 0. So when this whole thing goes to 0, you have 6 on this side. And then if here is 3, yeah, this gives us what, 6b. Can you see that? When you put 3 here, 3 minus 3 is 0. Multiplying 0 with a will go away. And we plug in our 3 on this side. It gives us 6b. And the left-hand side is 6. So we can divide here by 6, divide here by 6. And b is equal to 1. When b is equal to 1, we can also try and come back to this equation here and say that if we put negative 3 here, can you see when we put negative 3 here, the opposite of this positive 3, if we put the opposite sign there, this whole thing will go to 0. But here it's going to be negative 3 minus 3, which is going to be 6. On this side, this 6 will come equal to what? A into what? Negative 3 minus 3. Can you see that? Which gives us 6 is equal to negative 6. A. We divide it by negative 6, divided by negative 6, and we get a is equal to negative 1. So we've been able to solve that and saying that our 6 over x plus 3, x minus 3, which is a partial fraction, is the same as the a. What's the a? Minus 1 over x plus 3. And then what's the b? Plus 1 divided by x minus 3. So anytime we see something like this, we are saying that's the same as that. That is the first method for partial fractions, where you have linear factors in the denominator. Please, I hope this helps. I hope this helps. That's the first method. Now let's look at maybe the second method. And the second method says you might have a repeated factor, I think. Yeah, there's a repeated factor. So the repeated factor will look like something like this. Sorry. You might have a question like, excuse me. We are looking for a repeated question, a repeated factor is the next one. Okay, the repeated factor is the next one. Okay, so you have, let's say, 1 divided by x plus 2, x minus 1, all squared, like this. You can see that this factor has been repeated. That is a clue that you have to use we have to apply the what? The second method. So here, what we do is to take, because this is linear, can you see this is linear? We take a constant first and divide it by that linear. Now, even the repeated thing is also linear. Can you see that? It's linear. So we can take b first, right? With the first linear. This thing is repeated, but it will take the first one, plus another variable, but it will take on the whole repeated thing, like that. All right? It's like that. So I can say that method 2 is an extension of method 1. Can you see that? Because we are still having a constant variable, divided by one of the linear term. The second constant variable divided by the one of the repeated term, plus the third constant divided by the whole repeated term. And we're going to apply the same thing here. We can see that we're going to look for the LCM, right? This side is going to be 1 all over x plus 2, x minus 1 all squared is equal to what? We look for the LCM, which is going to be x plus 2 and then x minus 1 all squared. Can you see that? So that this will go into all that is going to just give us a. Can you see that? Yes, and this is no this here, we're going to all of that is the a multiplied by the x minus 1 all squared, plus this, we're going to everything, is going to give us b into x plus 2 and x minus 1. All right, plus c will go with the x plus 2, like this. Take the white color. Now we can see that this denominator and this denominator are now equal. So the denominator 1 should be equal to the a into x minus 1 all squared plus b into x plus 2 x minus 1 plus c into x plus 2. Can you see that? Because we said that this x minus 1 all squared is this. So the x plus 2 need to multiply the x. And that's what we have done. Now, if we put 1 here, why 1? Because it's negative 1. We put the opposite of it here. This whole thing will go to 0. So we're going to 1 is equal to 0. But we put 1 here, we're going to get plus 3b. Right? Can you see that? No, sorry. We put 1 here, we get 3 here. Put another 1 here, it goes to 0. So that means this whole thing also goes to 0. Plus, we put 1 here, we're going to get 3c. So it's going to be 3c. And then we know that 3c is equal to 1 and c is equal to 1/3. Can you see that? The next thing we're going to do is to plug in. We already did x equal to 1. We look at this plus 2 and put negative 2 there. Can you see that? We put negative 2 there. So we have, we put negative 2 there. When we put negative 2 here, we're going to get 1 is equal to this negative 2, right? We're going to get negative 3 squared, right? Negative 3 squared. So we're going to have negative 3 squared, and there's an a. 1 is equal to a into negative 3 squared plus. Now, if we put negative 2 here, this whole thing goes to 0. Negative 2 plus 2 is 0. And then 0 multiplied by all of that is 0. And then it makes the b2 also go away. So plus 0. And we put negative 2 here, right? We put negative 2 there. That also goes to 0. That also goes to 0. And we are going to have 1 is equal to a into 9. So we know that we divide it by 9, we're going to get a is equal to 1 over 9. So we have been able to get our a over 9. We've been able to get our a over 9. All right? We've been able to get our a over 9. And then we have also been able to get our c. Now, how do we look for the b? How do we look for our b? All right? How do we look for our b? Now, what we can do is to expand, right? We can be able to plug in. Now we have 1, all right? I don't know whether we have enough space. Sorry about this. But on this left-hand side, all right? On this left-hand side, we can plug in. If we plug in our a and b, all right, does it help us to be able to look for our c? Let's take a look at how we can be able to do that. Because plugging in our a to be 1 over 9 here, and our b to be equal to, our c to be equal to 1/3, doesn't help us to solve the problem. I don't know whether you get what I'm trying to say. Because we want b. And if we want b and we choose any of these numbers, maybe we choose a number, okay, we can also guess. We can take any number. Let's say x is not, we're not choosing the x is equal to 1, neither are we choosing x is equal to negative 2. All right, let's say x is equal to negative 1. All right, let's say x is equal to negative 1. When x is equal to negative 1, this side is still 1, right? This side is 1. Is equal to the a. Our a is 1 over 9 into, this is negative 1. So that's going to give us negative 2. Can you see that? Negative 2 all squared. Are you there? Plus our b, right? Our b we don't know, but we put b there. And then we remember that we said we are going to put in what? Negative 1. Our x is negative 1. So if here is negative 1, this is going to give us negative 1 plus 2. And this is also going to give us negative 1 minus 1. And then we have our c that we don't know, right? We have our c that we know, plus 1 over 3, plus 1 over 3, 1 over 3 into what? Negative 1 plus 2. Negative 1 plus 2, like this. Now we have our 1 is equal to 1 over 9 into 4, plus b into, this gives us 1. and this gives us negative 2 plus 1 over 3, 1, like this. So can you see that this is giving us a number? Like we're having a number, let's say 1, we're having a number that is 1 is equal to 4 over 9. Can you see that? And this whole thing here is minus 2b, minus 2b, and then this whole thing is plus 1 over 3. Now we can multiply each side by 9. So this is going to be 1 times 9 is equal to 4 over 9 times 9 minus 2b times 9 plus 1 over 3 times 9. And this is going to give us 9 is equal to 4 because this cancels, minus 18b plus this cancels to be 3. Now we are looking for b. So 9 will stand here, the 4 will go, minus 4 is equal to minus 4. Then the 3 also come, minus 3 is equal to minus 18b. Can you see that? We're going to get, this is going to give us 5 minus 3. 5 minus 3 is going to give us, 5 minus 3 is going to give us 2 is equal to negative 18b. We divide it by negative 18, divided by negative 18, and then our b is equal to negative 1 over 9. Negative 1 over 9. And then that means our a, we said, is 1 over 9. Our b is negative 1 over 9. And then our c is 1 over 3. So that's how we use the second method to solve repeated factors in the denominator. All right. Now let's look at the third one. The third method is when we have a quadratic. Is when we have a quadratic in the denominator. We have a quadratic. Sorry, we have a quadratic in the denominator, right? You have a quadratic in the denominator. So let's take a look at an example. Like maybe we have 3x plus 1 divided by x minus 1, a linear, and then a quadratic term, x squared plus 1, like this. We said that the first thing we do, because it's a linear, we'll give it a constant divided by that linear, plus, because this is a quadratic, it's going to be bx plus c divided by that quadratic, like this. All right, now, can you see this is a fraction? That's a fraction, and what's in the middle is an addition. We apply the rules. It's going to be a multiplied by x squared plus 1. This multiplies all that. Plus, this multiplies that x minus 1, multiplying the whole bx plus c, divided by the x minus 1, also multiplying the whole x squared plus 1. And then on this side, we still have our 3x plus 1, divided by x minus 1, x squared plus 1. Like this. Now we see that the denominators are the same. The denominators are the same. And if the denominators are the same, it means that the numerators are also the same. It means the numerators are also the same. So we know that our 3x plus 1 is going to be equal to a into x squared plus 1 plus x minus 1 bx plus c. Like this. Now we can say that if x is equal to 1, right? When x is equal to 1, we're going to get 3 into 1 plus 1 is equal to a into 1 squared plus 1 plus 1 minus 1 into b times 1 plus c. Can you see that? So this gives us 3. This is 3 plus 1 is 4 is equal to, this is 2, right? This 1 plus 1 is 2. So 2a. And then this goes to 0. Can you see this is 0? So once 0, this multiplies, everything goes away. That means that our a, we divide it by 2, we divide it by 2. Our a is equal to 2. Can you see that? Our a is equal to 2. Now, we can be able to guess some number. We started with x is equal to 1. Can we also say that when x is equal to negative 1, we get 3 into negative 1 plus 1 is equal to a into negative 1 all squared, right, plus 1, plus negative 1 into b into negative 1 plus c, like this. And when we do that, we are going to have here to be negative 3. This is negative 3 plus 1. It's negative 2. It's equal to this 1 plus 1 is 2. So this gives us 2a. But remember that our a is 2. So we can put 2 inside there. Plus, this gives us negative 2. So we have negative 2 multiplying negative b plus c inside. Can you see that? Now we're going to have, we're bringing it here. Negative 2 is going to be 4. Are you there? This will multiply this, we get plus, right? This negative 2 times negative b is going to be plus 2b, and negative 2 times c is going to give you minus 2c. So we are getting something like a simultaneous equation. I'm going to move here. Now I'm getting negative 2 on this side is equal to 4 plus 2b minus 2c, right? So this negative 2, the negative 4 can come here. We have 2b minus 2c. That means that we have negative 6 is equal to 2b minus 2c. Therefore, 2b minus 2c is equal to negative 6. Can you see that? Then we can also pick another value. We can say that when x is equal to 2, or when x is equal to 0. Can we try when x is equal to 0? When x is equal to 0, the left-hand side is going to be 3 into 0 plus 1 is equal to, the right-hand side is going to be a. Our a is 2 into 0 squared plus 1. Can you see that? Plus 0 minus 1 into b times 0, which is 0 plus c. So inside is going to be c. And we're going to get 0 plus 1 is equal to 2 into, it's going to be 2 into 0 plus 1, which is 1, plus into negative 1 and c. Can you see that? Here gives us 1 is equal to 2 minus c, right? And then we are going to have 1 minus, this 2 should come, minus 2 is equal to negative c. And we're going to have minus 1 is equal to minus c, and therefore c is equal to 1. Can you see that now we have our a? Our a is actually 2. Our b, we don't know what our b is. We can go and plug this c is equal to 1 over here, which is going to give us 2b minus 2, right? Because c is 1. Minus 2 is equal to negative 6. So that 2b is going to be negative 6 plus 2, which is negative 4. And then the b is going to be negative 2. So b is negative 2, and c is equal to 1. Now, what do we do? It means that this whole 3x divided by what we're told to do, 3x plus 1 divided by x minus 1 into x squared plus 1 is the same as our a. We started here, don't forget a, which is 2, and we divided by this, x minus 1, and then plus our b. What is our b? Plus our bx. Our bx is, b is minus 2x, plus c. C is 1, and we divide everything by x squared plus 1. So we're saying this is the same as that. I'd like to bring this particular comprehensive lecture to an end, but I hope you enjoyed this session, and thank you for watching and being patient with us to have this comprehensive lecture together. If you are a new subscriber, you're somebody new to this channel, please do us a favor by subscribing and turning on the notification bell so that when we do a video or any kind of content, you will not be missed out. You will not be missed out. But if you're already a subscriber, we want to say a big thank you for supporting this channel. We'll come to you another time with another video, but before we meet, take care, and I'll see you later. Bye.